Okay. I want to thank you all for being here at this workshop on clinical ontology development. And I think we still have a few more people who come in, but I think we'll start with some of the introductions and get that on the way. So this tutorial is part of the dissemination activities sponsored by the National Center for Biomedical Biomedical Ontology, NCBO, and has been organized by the Department of Human Genetics at Emory University. Dr. Rani Singh is an associate professor of human genetics and pediatrics and director for the genetic metabolic nutrition program at Emory, and is leading a pilot project in the area of newborn diseases and long-term follow-up that will develop a prototype system and models for the collection and analysis of data in this relatively uncommon area of inborn errors of metabolism. Now, briefly, the agenda for today, the morning session will focus on a tutorial by Dr. Barry Smith, and in the afternoon we will be dealing with the work being done by the project team here and looking at the ontology for newborn screening and translational research. Before I hand it over to Barry, I want to say a few words about Barry, and also we'll get the introductions going. Barry, it's a privilege to have you here for this tutorial, and I've known Barry for many years now, and he's always been an inspiration in this work. He's brought a rigor to this to the development of ontologies, and it's always been very positive having his feedback on many of the projects I've worked. He's a philosopher, a distinguished professor and holder of the Julian Park Chair of Philosophy at the University of Buffalo, and is a very prominent contributor in both in the theoretical and applied aspects of in research in ontologies, especially in the biomedical domain. He is responsible for the formation of the OBO Foundry, which is a very widely recognized and respected open source ontology group. And he's a principal scientist at the NCBO, scientific advisor to the Gene Ontology Consortium, and principal investigator on several projects, including the protein ontology and infectious disease ontology projects.
Good. So there are two parts to this day, as I see it anyway. The first part in the morning, I will present quite a lot of information about how I think you should see ontology building in order to make it most useful for your purposes, and then also how you should actually build your ontology. And then in the afternoon, I want to give you some feedback about what you've been doing so far. And I warn you that I'm very often not very positive. But this is a hit and miss affair. So sometimes the criticisms that I make have proved to be very beneficial, and sometimes they've created enemies. But the enemies of my enemies are my friends. So in the long run, I do in fact accumulate more friends. So we're here because the project here at Emory and in Atlanta more generally involves an ontology component. And like many other projects throughout the world, and ontology has been, in many of these projects, successful in different ways. One of the problems is that because of the success of ontology, more and more people are building ontologies, and most of these ontologies are useless because they've been built too quickly, they've been built on an ad hoc basis, they've been built by some local group without considering what other people are building, and very often they have repeated building ontologies which already exist somewhere else. And so part of my mission with the OBO Foundry, which Sivaram mentioned, is to try and bring an end to this process where people are reinventing ontologies every Tuesday. Now, the starting point for all of this is the following story. If you do a search on PubMed, and this was done by Olivier Gordonrider some years ago, you will see a quite remarkable increase in occurrences of the word ontology in PubMed abstracts. There is always a lag, so if you do this in 2008, the 2007 pillar will be shortened. But if you continue, this was done in 2010, and you can see that still we are on an upward flowing curve. So there must be something that is behind these very, very simple statistics. And if we examine the statistics more carefully, which is what Bodenreiter did, then you will see that nearly all the occurrences of ontology in PubMed are occurrences of references to just one ontology, which was the gene ontology. The gene ontology overwhelms all other ontologies, including SNOMED, even including MESH, from the point of view of the use of the word ontology. Now, this is not all too surprising for SNOMED and MESH, because they don't contain the word ontology in their names. But it is surprising when taken more generally. Whatever the underlying reason for this growth in ontology-based research in medicine might be, the gene ontology seems to be the principal vehicle, the principal example of a movement which has captured the reason for this success. Now, the gene ontology is a rather simple hierarchy. Initially, there were just two relations joining together terms. So we can see the terms here. Cognition is a neurological system process. That means that every instance of cognition is an instance of a neurological system process. In addition to these is-a or subtype relations, the gene ontology also has part-of relations. And now they've added more relations concerned with regulation. But still, it's a rather simple hierarchy. However, there are very many ways in which this superficial simplicity is outstanding when compared to some of its competitors. First of all of the terms in the gene ontology have definitions. And these definitions have been checked for biological accuracy. Secondly, the gene ontology has a very, very systematic versioning process, which means that as knowledge advances, so the gene ontology keeps pace. Gaps are filled, errors in the definitions are corrected, and so on. Thirdly, and most importantly, the gene ontology is associated with a huge body of annotations. What that means is that the gene ontology community has paid PhD biologists to read literature and to annotate that literature using Go terms. This brings a number of benefits. First of all, you can search the literature using the Go terms and find the connections between, for instance, functions of proteins in one particular area of literature, maybe in the neuronal system of shrimp, and similar phenomena in a quite different area of literature, maybe newborn infant neurological problems. Which means that the gene ontology, because it's being used so systematically for so many annotations of so many different kinds of data, has become a kind of switchboard for accessing the life science information that we have. So, $100 million at least, probably double that if you include the drug company investments and so forth, have been invested in this process. And over 1 million annotations. These are annotations created manually by experts. It's very easy to annotate literature by means of data mining, text mining software. The quality of those annotations tends to be much lower. These are validated, manually validated annotations. And the result is that this body, this huge body of annotated literature and annotated databases, it becomes a playground for a large number of unanticipated secondary uses. So the gene ontology was invented to annotate information about the attributes of gene products, but it's now being used to annotate all kinds of biological information. Now, the gene ontology was deliberately species neutral. it was deliberately multidisciplinary. So it wasn't created just by people working on model organisms or just by people working on neurology. It crosses different branches of biology. And then it's completely open source. There are no restrictions at all on the use of gene ontology, which means you can take the whole of the gene ontology and incorporate it into your own ontology for free. There are no licenses, no click-throughs. It's all completely open. Now, in this way, because people could take the gene ontology and incorporate it into their own resources, the gene ontology is contributing to a kind of connectedness of ontology resources. They become a kind of web. I don't want to misuse the word web. They become a network because the gene ontology is connected to all of them in very robust ways. Now, in this way, I like to compare the gene ontology with the standardization of the system of units in physics in the 18th century. Because everyone was using the same units of measure, all physics measurement results became comparable. And before that standardization, Atlanta probably had its own system of measurements. There was probably an Atlanta foot. There certainly was a Texas foot. So what we need is to move from the Atlanta foot situation to a situation where we're all measuring in kilograms. And that's what the Obo Foundry is trying to do. So there's some information now about the way in which the gene ontology works. So when you do a gene array experiment, then there are questions that you always need to ask. Where in the cell, what kind of molecular function, what kind of biological process? And the gene ontology provides natural language labels to describe the answers to those three kinds of questions. And then in natural language, because you want to do this in a way that human beings can understand, you want to do it properly. But those natural language labels are formalized. They are constrained in such a way that they can be captured by a computer. Now, I like to compare this with the way in which maps have legends. So consider these things as the legend to this map. This represents something that you find in the world. It's a very tiny granularity. This represents something that you find in the world. This is the key to that. And the gene ontology is the key to what goes on inside the cells of organisms, for instance. And map legends have certain characteristics. So they describe types, for instance, types of rock, types of river. And similarly, the gene ontology describes types. And then on the left, you have the instances of those types. And you can use legends not just for maps, but also for cartoons. And the ideal would be to have all the images in biology textbooks use the same labels. We are gradually moving towards that, certainly within disciplines, but we're not even close when it comes to cross-disciplines. So, ontologies are legends of data. That's the summation of this particular sequence. And if you do your legends right, then if you have maps of different segments of a given domain, such as the United States, then all the maps should be compatible with each other. You should be able to glue the maps together. And similarly, if you use the same legends for your data, then in principle you ought to be able to glue your data together to produce larger data. And I guess that's the goal that you have for your project. This should be music to your ears. And you can use ontologies also to annotate or tag or label images. And then you have questions like this. Now, so the gene ontology, I described it as a switchboard. You imagine all of the databases which have been tagged using gene ontology terms, and they all become connected. So you can find everything relevant to the Holiday Junction helicase complex in every database, and there are many of them which have been annotated using the Go, immediately. So you can search through 100 or 200 databases to find exactly what is relevant to your specific phenomenon of interest. you can compare images of the same phenomenon. You can pull in the images, again, by using the fact that gene ontology has been used to annotate different image corpora. So, the Go supports reusability of your data. It supports search by human beings. It supports comparison of data. It supports aggregation of data. And it supports reasoning, both by human beings and also, most importantly, by machines. And that's the point where we're beginning to make progress. That is, I think, what we will get in the future. But unfortunately, the quality of the data and the quality of the ontologies at this stage, and most importantly, the lack of consistency in the ontologies at this stage, is serving as an obstacle to the real potential of machine reasoning with life science data. So this is a picture of the gene ontology, just a small fragment with the new relations. So we have ISA, part of, regulates, positively regulates, and negatively regulates. And this is the transcription. And I won't go through this picture. You can go through it yourself. There are something like 30,000 nodes in the gene ontology at this stage, divided into 3 groups: biological process, molecular function, and cellular component. So what we want to be able to do is to carry out reasoning across clinical and translational data, which means that we can supplement clinical trials which are carried out in vivo with virtual trials which are carried out by using the data. And in the end, I tend to be cynical and skeptical and negative and angry about most things, but I truly do believe that we will have this, maybe even in my lifetime. But it's going to be much more difficult than many people think. All right, so this goal, this vision of virtual biology is achievable only if we can get the data, if we can compare the data, and if we can integrate the data. And this is only going to be possible if we have what physicists had already in 1793. I don't know why this slide was left over. So Sivaram described me as a philosopher. I'd like to describe myself as somebody who used to be a philosopher. I'm now an ontologist. It happens that ontology used to be part of philosophy, but so did psychology. So did physics. All right, I'll ignore that. So, I talked about maps and I talked about legends. Maps represent instances in reality. Legends represent the types which those instances instantiate. Types of rock, types of mountain, types of river, and so on. This is how we need to see the world if we're going to do ontology correctly. There are types: cell, organ, organism, binding, cell division, disease process, and so on. There are types. And then there are instances. My disease, my coughing, my lung. They are mine. They are here and now. So instances are here and now. Types are universal. They're everywhere. In principle, anyway. Now, when we have an ontology arrow connected to boxes, we're connecting one box representing one type with another box representing another type. For instance, cell membrane, part of cell. That's what ontologies are made of. Axioms, linking terms representing types by means of relations between types. And because these are universal types, then we can use them to reason. Every cell membrane is a part of some cell. The computer can reason with that. And this is the way in which the is and part of relations should be organized. So one of the best examples of an ontology in the life sciences domain is the foundational model of anatomy, the FMA. We have on the horizontal plane the part of relations, So the interlobar recess is a part of the pleural cavity, which is a part of the pleural sac. That's one stratum. And then on the vertical plane, the interlobar recess is a serous-sac cavity subdivision, which is an organ cavity subdivision, which is an anatomical space. The terms in the top are highly general terms. The terms down here are the terms that you probably would find when you were doing medicine. You need the highly general terms in order to make sure that you've organized the ontology in a way which is going to enable coherent reasoning. Yes?
Your very first slide talked about controlled vocabulary versus ontology. Do you want to comment on that?
Yes, so every ontology should be a controlled vocabulary. And the International System of Units is an example of a controlled vocabulary. What this means is that it forces you to use certain terms with certain meanings, certain spellings, always, consistently, like everybody else. But an ontology is a controlled vocabulary with two extra ingredients, I believe. One ingredient is the is-a hierarchy, which is the taxonomy. There's more and less general type in a tree. And then, in addition, you have other relations. Part of is just one relation, but there are other relations. For instance, regulators. Regulation of sleep regulates sleep. Ontology very often is not rocket science, and that's a good thing. It's a tragic thing when you see how many mistakes people make. So this is a taxonomy, which is probably biologically inaccurate, but you get the idea. Here we have much more than a taxonomy because we have these extra relations. And also, we missed out very many nodes in the tree. Good, now let's change tack here. So we're moving from the gene ontology to SNOMED, ICD, and other controlled vocabularies. I not only believe that we will have virtual clinical science, or anyway, we will have an important contribution to clinical science coming from the computer. We already do, in fact, have beginnings of that. I also believe that we will have a contribution to the care of patients coming from the computer. And maybe we even have that to some degree in Denmark, maybe. The problem here in the United States turns on the fact that we have, when we're dealing with clinical care, the role of competing industrial vendors of patient software. And I'm talking now particularly about electronic health record systems. There are multiple electronic health record systems which exist in different hospitals, and there are multiple other systems for keeping track of health-relevant data which are used by labs and by organizations like the CDC. And patients move around between hospitals and doctors, and as they move, then it's unlikely that their data will move with them, in part because the hospital they move to uses a different system. Now, there are various steps which are being explored to try and solve this problem. I'm not going to talk about all of them. One of them is called CDA. Another is called SNOMED. ICD already constitutes a kind of solution to this problem. But the problem is, how do we ensure that data moves to the patient? And if you do a Google search for the phrase, the data model that nearly killed me, you will see that this is a really serious problem in certain circumstances. Now, there are two problems here. One is that we sometimes are involved with multiple hospitals or with multiple care institutions at the same time. And the other is that as we grow older or as we move house or whatever it might be, we are engaged with different hospitals at different times. Both of these are the same kind of problem. So how could we link electronic health records which are based on different systems, which are proprietary systems so that we can't unlock them, in a reliable, trustworthy, and useful way so that both of the systems can understand the data which is transported backwards and forwards across time or space? This is a problem which, in a way, ICD solves. The ICD is an international classification of diseases which every hospital in the United States in practice uses, but they use it for billing purposes and for not really much else. So while this would be a good solution, its practical realization is not very good because the billing process is not necessarily an adequate picture of the health relevant process. It's certainly not an adequate picture of the research relevant process if we want to do clinical research with health data. The ICD also has the positive feature that it exists in multiple languages, so that it would work even if you moved to Spain or Mexico or Texas or somewhere where people speak Spanish. The problem with it is that the billing process corrupts the data just to a worrying degree. Another problem is that there are no definitions of the terms in ICD, really. Which means that you can't use it, for instance, to do quality assurance by means of computers. You can't test the consistency of the data. The hierarchies in ICD are inconsistent, which means that you get problems that different communities code in different ways. Again, it's hard to reason with the results for all of these reasons, and that means that the secondary uses that we want from clinical data, particularly the huge amounts of clinical data that we get from ICD, are relatively unavailable. We can use ICD for public health statistics, but we can't use it for the kinds of translational research that we're interested in this room. Now, there is a plan called ICD-11, and I know the people who are involved in this plan, they are certainly the people with immense competence when it comes to addressing these problems. They want, with the ICD-11 revision, to solve the problems I mentioned by using ontology technology, semantic web technology, and by building ICD-11 in such a way that the classification will be viewable from different sides. So you will have one view of ICD data, which is the billing, and you switch the box, as it were, and you'll have another view, which is the public health statistics view. And then you'll switch the box again, and you'll have the research view. And there could be other views. There could be a SNOMED view, for instance, because there is a commitment by SNOMED and ICD that the two will be compatible with the ICD-11 revision. This is an amazing plan, and if it's realized, then it will mean that ICD data is far more valuable than it is currently. I'm skeptical as it will be successful, however, because this is a really difficult plan. Already, the human factors involved in bringing about compatibility between ICD and SNOMED are enormous. These two groups are large and difficult to manage. And to manage them in such a way that they do the same thing independently is going to be a very difficult achievement. But still, we should bear this in mind. ICD-9 is what is currently used in the US, although for some years ICD-10 has been federally mandated. So ICD-11 may involve a big jump also in that respect. So SNOMED. SNOMED is another ideal solution. SNOMED is a single universal clinical vocabulary. It's already used in the United Kingdom as the basis for the National Electronic Health Record. There is a United Kingdom law which says that all terms used in an electronic health record have to be included in SNOMED, which means that SNOMED includes the term injury due to crossbow accident. So this is good. It's all there. And it's an international standard with a lot of money in all perpetuity, since multiple governments have committed to pay large amounts of money each year, forever. And then within the countries that pay, SNOMED is free, which is good, although not perfect, because some countries don't pay. And again, like ICD, it's multi-language, although not every language, and not every language it has a perfect SNOMED translation. But the con factor still remains. So SNOMED is huge, and it has some redundancies which flow from the fact that over time it has incorporated chunks of terminology from other sources, particularly from England. And those incorporations are not always smooth. Also, it's gappy. Even though it's so huge, there are still gaps. It contains many examples of terms which are putative synonyms, but which are not synonyms, or which might be synonyms. There's a lack of clarity in that respect. There's no solid interpretation of the relations. So I talked earlier about Isa and Kartov. That's really hard work to get those relations well defined and well used. And SNOMED still has not really succeeded in doing that work. And there are many idiosyncratic relations. There are many mixtures of ontology with epistemology. I'm going to talk about this later. But if I talk about an absent nipple, that is not a special kind of nipple. It's a special kind of knowledge. And SNOMED is not really good at getting that right. Also, SNOMED contains numerous composite terms, such as the test for X, without the constituent terms being part of SNOMED. So you can have a test for something without the something being there. And this is so even where the X is obviously clinically important. And that's because people need test for terms to code more often than they needed the terms coded. And so the test for terms got in there, but there was no pressure for the other terms. But if you're going to reason with this consistently, then you need to have those other terms there. Now, this means that coding with SNOMED is unreliable. Different groups code differently. And that you can see why. So the traps are so obvious. It's hard to change SNOMED. It's hard to have errors fixed. There are some very clever people in the leadership of SNOMED who commit to making those changes, but then the commitments get lost in somewhere. And it's not clear that there is a strategy for evolutionary improvement. So what we need if we're going to do this job properly is to find ways of measuring the quality of what we do and of making changes and testing them. And those changes which give positive results should be implemented more globally, and the others should be dropped. We need evolution. And it's not clear that SNOMED has that. All right. But because of this problem of redundancy and because of the problem of failure of consistency of coding, SNOMED doesn't provide a good solution to the continuity of care problem. It wouldn't even provide such a solution if the electronic health record systems that we had were annotated using SNOMED. But even that would be difficult because of the proprietary issues. And it doesn't provide continuity of care if you move to Germany, for instance, because Germans don't like SNOMED. All right, now there is one other example which is of great relevance. It's the Unified Medical Language System, which is the NLM umbrella for 100 or so clinical vocabularies, including SNOMED. The idea is that you have these UMLS systems, you use them to create a snapshot of the patient's condition, and then you can move the snapshot, which will be updated progressively backwards and forwards between hospitals as the patient moves. Now the problem is that the UMLS doesn't work because some hospitals would use some parts of UMLS to make the snapshot, and other hospitals would use other parts, and you don't get the consistency. You end up with people shaking hands who are still in different rooms. So the UMLS is actually not a single system, it's a collection of terminologies, and it will not solve the problem of translating between different bodies of knowledge. It says it will, but this is just a quote from the UMLS. This is a picture. The Unified Medical Language System is actually 6 doctors, all of whom have different ideas about what's going on the side of the patient. Now, this is really the second dimension of what I want to communicate to you today. The first dimension is there are instances in reality and there are types, and the ontology represents types. The second dimension is that there are theories and ideas and speculations and diagnoses on the part of clinicians and researchers and other people. And then there is the patient and the organs and diseases and cells and chromosomes of the patient. These are in reality. These are what we represent. These are in reality too, but they are representations of what is in reality. Now, the basis of the confusion in SNOMED between epistemology and ontology is that they're trying to code all of this, just as UMLS is trying to code all of this. Well, what we need to be doing is trying to code this, because there is only one of this. All right. Now, if sometimes I say SNOMED and so on is all very well, but clearly we need to start again from scratch. We've done it all wrong. There are many arguments against this. One argument is that we have a huge amount of legacy data, which we will always need to use. But we need somehow to have a strategy for solving this problem. And I'm interested in the strategy solely from the point of view of creating a system for annotating data, whether it be clinical data in hospitals or whether it be research data in labs, in such a way that we can get this continuity solved. We can move data around, and it will be understandable in the same way, and it will be coded in the same way by different communities. And it will be done in such a way that computers can reason with it. Now, what we need is prospective standardization. And what this means is we have things now which work, but they are not working well. The coding consistency is very low. But we know what would work. So let's try and find a strategy whereby incrementally what we do now gradually moves closer and closer to what would work. That's prospective standardization. We are not Napoleon. We cannot impose French units of measure on the entire world. Now, prospective standardization is not going to work for everybody because there are people who just will not buy into the new standardization. So what we do is to create a body of people who believe in it and who say, we are going to do it right, step by step. We'll use the good bits of SNOMED. We'll use the gene ontology. We will pick those standards which we think are accurate. We will not use the other bits because we can see that they're confusing and false and liable to generate inconsistency. We'll pick the standards we like, and we will develop them. We'll make them better and better and better. And as the success of this approach becomes apparent, other people will join. And gradually, the size of the consortium of people who believe in the standards will get bigger. But this is the open boundary idea. Now, in order to do that, you need some kind of governance. So and I'm going to give you more details about this later, but just to anticipate. supposing that somebody said, well, we have OnStar, is that how you pronounce it? We have OnStar, we think this is a high standard thing. We would like to join the Open Foundry too. Well, someone has to make that decision. We have principles, which you can read on the web and which you can see examples of. They're rather simple. But it turns out that people think they satisfy those principles, but they haven't. Or that people have satisfied the principles, but then they retire, and they're replaced by people who don't care. And so there has to be some kind of top-down governance, which is a rather light-handed approach in terms of the people who do it, but which is rather tough when it comes to respecting the rules of the common architecture. And we'll go into that later on. Now, I'm going to give you some examples of the principles now. These are examples which, many of them are a bit like driving on the right side of the road. In other words, it's not because it's the right way to drive that you should drive on the right. It's that you have to choose either the left or the right. And once you've made that choice, you should stop worrying. So think of the principles for best practice here in those terms. There are many people developing ontologies, some of them in biomedical domains, who think that anything goes and that you don't need principles. You can just use the power of the ontology syntax and the power of ontology reasoners in order to get benefits. Those projects tend to be very, very short-lived projects. The gene ontology is by far the oldest ontology ever. It's already 12 years old. And it's still growing. And that's because it paid attention to some of these principles from the very start. It pays attention to all of them now. Okay, so the first set of principles have to do with the fact that ontology and bioinformatics more generally is a multidisciplinary enterprise. So there are people here in this room from the database community, from computer science, from genetics, from bioinformatics, from medicine, and they all have their own terminologies. And if we're going to work coherently together, then we need to make sure that we're aware that we have these different terminologies. And we need to make sure that we're using words when we're using them in technical ways in the same way. Now, these are some examples of words which are often misused when it comes to ontology development. And I can talk at length on for each of these. The three most important ones are type, instance, and representation. And I hope that you've got by now the importance of these three terms for what I said. We can distinguish three levels. First of all, there are the patients on the ground, the patient's organs, the patient's bedding and drugs and breathing and coughing. Then we have the ideas in people's minds about the patient, the ideas of the doctor, for instance, or the ideas of the patient. And then, at the top, we have what we can think of as published representation. The ideas on level 2 have become public. And databases, published literature, patient records are all examples of public representations. And the ones that we're interested in today are ontologies. Ontologies are ideas made public. They're what we think about the patient made public, published, formalized, specified, defined. And again, those three levels are very often confused in ontology talk. There are more confusions connected with the word concept than any other word I can think of in the realm of ontology discussions. And so the first principle, I don't think I'd write this down here, the first principle is that you should never ever use the word concept. And you will sleep better, you will. Now, I'm going to use the word entity now and again. An entity is absolutely general. It's a term which refers to anything which exists, including a database or a debt or a country or a gene or a cell. Anything which exists is an entity. Some entities are types. They're general. They exist all over the place. And some entities are particular. For instance, me. And there are entities on all three of the levels. So my thoughts are entities. Your thoughts are entities. My words are entities. We have type versus instance. Types are described in science texts. That's what science is all about. It's finding out the general structure of reality. Instances are described in diaries or in your experiment logs or your electronic health record. Now, ontologies are interested in generals. They're interested in types or kinds. And so we can think of an ontology as being like a catalogue. It's a catalogue of the kinds of entities that you have in your factory. And a database is like an inventory. It tells you how many dust collector fans you have in your factory. So I'm repeating this over and over again because this really has to be burned into your minds. An ontology is a representation of types. We do experiments on instances to find out what is typical of those instances. And we give names for those typical features of the instances, and those names go into the ontology. And now we can define an ontology. An ontology is a collection of representational units, terms, preferred terms, those things in the boxes. Typically, the terms will be drawn from a natural language, but we could have an ontology in which the terms are in a formalized language. And increasingly, we're going to have two views of each ontology, the natural language view and the formal view. Those terms are intended to represent types in reality and relations between those types. And the relations which the ontology represents are the non-rocket science relations, the trivial relations. For instance, a lobe of a lung is a part of a lung. That would go into the ontology because it's universally true. You never have a lobe of a lung which is not part of the lung. Now, of course, even here we have a problem because you could cut off the lobe of the lung. But unless you insist, you can just trust me. There is a solution to that problem. Finally, the ontology is it's always in keeping with established science. It grows as established science grows. So if we have some speculation in textbooks that there is something about this particular kind of lobe of lung which does this and this, we don't put that into the ontology. We only put things into the ontology when they correspond to established science. This is important, otherwise, again, we would have forking. The job of the ontology is not to replace science. The job of the ontology is to serve as a reliable switchboard connecting different scientific communities. And if you give the speculations of one group a role in the ontology, you are defeating the purpose of the switchboard. So, there are types and there are instances. Now we could define a domain. Each ontology should correspond to a specific domain. A domain is a portion of reality that forms the subject matter of a single science or technology or mode of study and so forth. So proteomics, epidemiology, infectious disease, and so forth. These are all domains. The idea behind the oboe foundry, which I will talk about later in more detail, is that there should be one and only one ontology for every domain. Then we avoid the need to map ontologies. Everybody knows where to go for ontology information. But again, there's a problem here. What is a domain? So is shrimp proteomics a domain? Now again, I have an answer to that question, which I'm going to give to you. And this is called the homesteading answer. If you are working on shrimp proteomics, you build an ontology in conformity with the principles of the Obo foundry. Which means it has to be compatible with the protein ontology, which is one of the Obo foundry ontologies. It has to have users independently. Then you get your patch of South Carolina or wherever it is. You get your patch of ground for as long as you can maintain it. But if no one cares about shrimp proteomics, or if no one needs a shrimp proteomics ontology, then there will never be one. So what domains exist is a matter of what people need. It's not something which you can work out in advance. I guess I'll pause for questions there.
So, in other words, what you're saying is, even though in reality there are overlaps between domains, for your purposes, you keep those domains for your purposes and start working on those domains.
So, if we let people homestead land without paying attention to the need for fences, there would be chaos. Which means that we're going to have to find, this is part of the governance process of the Obo foundry, we're going to have to find a way of resolving border disputes. And we have that. So that the protein ontology contains protein complexes. There are some protein complexes which the gene ontology includes under the heading of cellular components. So those protein complexes are targeting two different ontologies. Now, fortunately, these are groups of people, both of whom are part of the Obo foundry, and they are resolving that. It's not a trivial matter. So the gene ontology has many users who are comfortable with the idea that they find those protein complexes with Go icons. But this is one of those areas where work has to be done on a level of governance. And what that work involves is bringing people together for meetings, and then we debate what is the appropriate treatment of the entities in question. Good, so one issue which arises here when it comes to the needs that ontologies are designed to address. Sometimes people will have a project, and this may be the case of the OnStar project, which has needs, ontology needs, which belong to multiple domains. So you may need gene ontology terms, you may need terms for anatomy, protein terms. And then you create what we call an application ontology. So the gene ontology is a reference ontology. It's designed as a stable collection of relations between terms which form a stable part of the study of gene products. And it grows with time as the science of gene products and associated sciences develop. The foundational model of anatomy is a reference ontology for mammalian anatomy. It doesn't grow very much because mammalian anatomy is pretty stable. But those reference ontologies are maintained. The definitions are maintained. The IDs are maintained. The annotations are maintained. You may need to take some terms from there, some terms from there, some terms from there. Keep the IDs so that as those terms are maintained by the reference ontology groups, you will get the benefits. But you put them within your own framework. And we have a strategy for doing that called myriota, which stands for minimal information for referencing an external ontology term. If you use the myriota strategy, you get the benefits of the reference ontology, but you have an ontology which serves your particular local application needs. And that's where we get domains which overlap with reference ontology. Now, a representation should be pretty clear. It's an image or an idea or a word which represents some entity or some entities. And ontologies are representational artifacts in just the same way that science texts are representational. And like science texts, they need to be updated. They need to have new editions because science grows. Representational units are those things which are the minimal representational artifacts. They are the atoms of representation, single words. And an ontology has to be built out of representational units, and those representational units in the ontology form a structure that mirrors the structure of the corresponding domain. So the idea is that a domain like the protein domain has one very high-level type, which is protein, and then a lot of lower-level types. And that hierarchy of types in the ontology mirrors the way in which proteins themselves are organized in reality. And this is one rather successful success story in this regard. Now, we use this thing to view the reality, which is the reality of chemical elements. So when we view the reality through this thing, we get the structure of the domain. So this is a kind of sophisticated pair of spectacles. And that's how the ontology should be conceived of. Actually, it could be here also. It's a way of viewing reality, a common way of viewing reality. You label the boxes in such a way that everybody can know what you're looking at when you tell them that you're looking through a certain box. So the ontology is here or it's here. The ontology represents the general structures in reality. Each box in the ontology corresponds to some type on the side of the patient or on the side of whatever is the reality that you're concerned with. Ontologies don't represent what's in your head. What's in your head is irrelevant. The ontology represents the types in reality. So only this part of the story is relevant. No one cares what was going on in the minds of Einstein when he invented relativity theory. What matters is what he wrote down on paper. So, ontologies are representations of types. There are some people, my enemies, who think that this is a really controversial proposition. In fact, for me, it's as uncontroversial as the proposition that when scientists write science papers or science texts, then they use general words. That's it. There is nothing more than that. And they use general words, of course, for things that they find in reality. They don't use words like pink unicorn, because there are no pink unicorns. So wherever scientists use general words, there's probably a type in reality. Maybe they made a mistake. They used to use the word phlogiston. They made a mistake. Sometimes scientists make mistakes. Ontologies will sometimes contain mistakes. We will correct those mistakes. But this, I believe, is relatively harmless and uncontroversial. There are repeatables in reality. Things that you can get many of. And then there are one-off things like Bill Clinton. There could only be one. And that's true of this cup. Although the cup type is repeatable. I don't know, hand wave. This hand wave is in particular. Now there is a problem here in that we very often use words for types to refer to particulars. So we could use HIV to mean a certain type of infectious retrovirus, or we could use HIV to refer to a collection of instances, very big instance, which is spreading through Asia or something. So you need to be wary of that distinction. One of the issues which we need to be very careful about when we're exploring OWL, which is the preferred ontology language, is that they are not always clear about this distinction. It doesn't do any harm from the point of view of computation, but it does do harm if you're not aware of the underlying strategy here. Now, we're coming to some OWL-relevant ideas more generally. So we're going to use the word class to mean one of these large collections. So HIV, considered as a large collection of instances of a certain virus, is a class in this terminology. And remember, what I'm doing now is I'm trying to give you preferred meanings for terms which will be used over and over again when you're doing ontology work, and which you will read in the literature. Now, some people will write things in the literature which involve use of these terms, but which have different meanings, or no meanings at all because they're confused. Usually when the word concept is used, there will be no meaning associated with this word. It will just be a lazy word. Very often the word class is used in a lazy way. So you should be aware. This is my preferred reading of this word. It gets pretty close to the useful meanings that you will find in the literature. So, a class A is the collection of all particulars for which A holds. So the collection of all viruses is the class virus. And again, you see an issue here which is time. Do I mean all viruses now? Or do I mean all viruses ever in the past, the present, and the future? That is a non-trivial issue. But this will do for the moment. So we have types, and we have collections of particulars, the instances of those types. And the standard term for the collection of particulars of a given type is called the extension of the type. So there are some classes which are extensions of types. The class of all viruses, the class of all people, the class of all tables, the class of all coffees, and so on. Then there are other classes, for instance, the class made up of this, whatever it is, and this. This is a class which is not the extension of any type. So there are many, many classes which are not extensions of types. And we call those other sorts of classes. And some people use the word natural kind for these things, extensions. So the Homo sapiens is the class of human beings, it's the natural kind. These other sorts of classes may be unnatural colligations of various. So the class of all diabetic patients in Leipzig on the 4th of June 1952 is an example of a class which is not the extension of any type. Any questions at that point? All right. So, OWL is a good representation of classes. Classes you can combine combinatorially. So we have here all diabetic patients in Leipzig on the 4th of June 1952 whose mother is called Maria and who eats in a particular restaurant every Wednesday when it's a full moon. You can do all of that with OWL very well. And there is much of that in SNOMED. SNOMED is a highly compositional language, and so the underlying description logic approach, which OWL represents, captures those compositional aspects of SNOMED very well. And this is good also for formulating criteria for candidates for clinical trials. And so the OWL resource is good for those kinds of combinatorial selection problems. Yes?
Can you comment on when a type becomes a class and when it does not?
Yes, so this is the question that I mentioned earlier. I want this not to be a problem. So again, the idea is that scientists use general terms, and the problem, actually, you are addressing a real problem here. When scientists are describing clinical trials, they may use a general term, like person with a nose longer than 2 centimeters who is a fan of rock music, to see whether there is any connection between noses and ears when it comes to ear damage through listening to loud music. And it may be that you have very long terms describing classes of people, and you want to say, I'm studying this type of person who has this kind of body features. I don't think anything turns upon that. There is this kind of person. We can do research on this kind of person. If you get interesting scientific results from doing research on this kind of person, interesting means transportable to people in other countries, for instance. then there is a type here. So the clue is not whether we can capture the thing in one word, because of course we could invent a word. Rocky. The clue is whether you can have interesting scientific generalizations, scientific laws. If you can have scientific laws which use a phrase, a general phrase, even a quite long one, indispensably in order to be formulated, then there is a corresponding type. But of course, you may 5 years later discover there is no corresponding type. You did a bad experiment. No problem. We fix the science. That's what we do all the time. Good. So, but there is a problem, which is the concepts problem. So there are some people who think that there are types, like people. There are classes. People who eat in the Emory Conference Center Hotel disco bar. And then there are concepts. And concepts have the feature that they don't have any members. So a cancelled oophorectomy, for instance, or an absent nipple, or an unlocalized ligand. Now, these are eigenate. There is nothing which these things refer. Nothing to which these things refer. There is no such thing as a cancelled oophorectomy. What there is a word which is used for perfectly good reason, but it doesn't correspond to anything in reality. And this is true for all of those cases. Phlogiston is a concept, they say. It's not. There is no such thing. We were mistaken. We were wrong. Get over it. Good. So, another principle. The principle of low-hanging fruit. Ontologies can and should contain absolutely trivial assertions. So the relation will often be trivial. This is a good thing. It's not a bad thing. You can do a lot of good work in compiling an ontology just by compiling absolutely trivial relations between terms which are important for your research. The computer can already get a lot of value from that, but the coordination of the members of your community will be of even greater value because they'll all be using those terms in the same way. And computers are stupid. Now, another example, this is a classic example of always drive on the same side of the road principle. Terms in ontologies represent types. There's a one-to-one relation between the term Homo sapiens and the type Homo sapiens, or the term cough and the type cough. Now, if this is true, and we're going to make it true, then every term in an ontology has to be a singular noun. A singular, general noun or noun phrase. If you look at mesh, you get nice things like National Socialism is a political system. Now, this is just a recipe for inconsistency. Inconsistency of spelling. So, terms in ontology represent types. Every term should be a singular noun. Now, the use-mention confusion. There was once an ontology, maybe it still exists, I will not name its name, but it used to define a mouse as a common name for the species musculus. And this is called the use-mention confusion. A mouse is not a name. The confusion is realized here. Swimming is healthy and has 8 letters. So, you wouldn't believe how many examples of this confusion there are in ontology work. And I will not mention the age of So, avoid confusing between the words, the things, and the things themselves. Avoid confusing between the concepts in your head and the entities in reality. And again, I recommend the word concept should just be not. In fact, there should be a concept tax. Everybody who uses the word concept should pay me $1. And if I use the word concept, I have to pay it all back. And notice that I didn't use it even once, just then. I mentioned it. I did not use the word concept. So this is, I don't need to mention this. So heparin therapy is defined by trial bank, or was, I'm sure they fixed it, I hope they fixed it by now, as an instance of a written or spoken designation of a concept. This is not a useful definition of anything. I noticed the misuse of quotation marks. Are they talking about heparin therapy, or are they talking about heparin therapy? So beware of terminological baggage. That's not a very good name for a principle. So the idea here is that if you're building a plant ontology, you're really only mostly interested in plant cells. And so the plant ontology, long ago, about 6 months ago, used the word cell to mean plant cell. Now that's a recipe for disaster because one day, very soon, the plant cell is going to need to explore bacterial infections in plants. And then they're going to have cells which are, in the ontology, plant cells, but which are bacterial cells. And so the international, I don't know whether they were reading my work, but the International Classification of Nursing Procedures in the old version defined water as a type of nursing phenomenon of physical environment with the specific characteristics. And so that is a bad definition of water. So they fixed it. Maybe I'm influential in some circles. Or maybe they just grew the necessary sensitivity that is necessary to do this work right. This is why you need human beings to do the work, who think. Every ontology term needs to be associated with some finite amount of thinking. Now, every term in an ontology should have a definition which should be human understandable. And in the course of time, this is the first thing to do, human understandable. In the course of time, you need a formal definition. Do the human one first.
What do you mean by formal definition?
That is a moving target, but probably for the purposes of this, on start to use owl. Yeah, so it means an owl definition. And that is a pretty unambiguous statement. There are always complications when you start looking at different languages, which are owl sub-languages, but for the present purposes, it's enough just to say. It's actually hard to get formal definitions which are equivalent to the human understandable ones, but there are people who know how to do it. And it's a long, long story. But it's not, the long, long story is going to affect the future. It's not going to affect the work we do now. Each term should have exactly one definition. It's a mark of a bad ontology. Any given term has more than one natural language term. So the National Cancer Institute Thesaurus has 3 definitions for the word cancer, which are inconsistent with each other. We understand why they do it. They want the word cancer to mean both disease and tumor. But you can't do that. A disease cannot be 3 centimeters in diameter. Now, I'm going to talk more about definitions. The definitions are one area where I think we already know how to do it rather well, quickly. You should avoid circularity. So it's a bad definition of a person to define a person as a person with an identity document. This is the way HL7 defines, still in some parts defines a person. And when Katrina hits, all those people suddenly lose their identity documents. And HL7 has to come to the rescue. So definition should never involve the term to be defined on the right-hand side. So this is an example of the definition of HL7. Stopping of medication. We all know what that means. is a change of state in the record of the Substance Administration Act from active to aborted. This contains so many things. So that the HL7 has two ways of dying. One way is the normal way. The other way is to be deleted from the database. Now, a good definition, a definition, in fact, which is a definition, should use on the right-hand side only terms which are easier to understand than the term you're defining. Otherwise, why have a definition? If the definition is more complicated than the term to be defined, as it is here, then the definition isn't helping anyone. Now, this is a rather sophisticated label for a principle because it's a generalization of the principle created by Tarski, who was a famous logician. But it's a good rule, and particularly if you're working with anybody who's involved in HL7, that E always means E for any expression. So dog means dog. Atlanta means Atlanta. It always works. Now you would think snow means snow. You would think that people would never ever break this rule. But this is everywhere in HL7. In fact, everywhere in data modeling. Data modeling systematically breaks this rule. Now maybe they have their reasons, but the consequences, and maybe the consequences are often good, but the consequences are sometimes bad. And in the medicine, it's often important to avoid consequences which are even sometimes bad. So, in HL7, medication does not mean medication. It means the record of medication. Disease does not mean disease. There is no disease in HL7. Disease means the observation of a disease. And a diagnosis in HL7 is the observation of an observation. Now, another rule is this. When you're building an ontology, you need to define all your terms, I say. In fact, that's not true. You will need to take some terms over from other ontologies where they may be defined. Eventually, you'll get to terms which are of such high level that you can't define them because they're already too basic. There's nothing more basic. So you shouldn't be afraid of acknowledging primitive terms. Maybe you don't need to define terms because everyone in your community knows what they mean. Ideally, you should take them from another ontology where they are defined. But there will always be some primitive somewhere in your hierarchy. That this is just an inevitable consequence of the principle that definitions have to be such that the terms on the right are more basic than the terms on the right. Yeah.
So, are you saying that some of those, let's say a person, a man, some of those, you won't have to because everybody else understand. If we go that far, that way, are there any rules to say who says this could be primitive, this needs to be defined?
I would suggest, so I'm giving you rules here. Very often these are rules of thumb. So in every case there are some issues, as I think I've made clear. I would say that where you're dealing with things which might be primitive, you're already dealing with things which are so basic that it really doesn't matter which way you go. So if you think you could find a definition of male, for instance, then, and you're happy with it, then use it. If you can't find a definition, then probably stick with just treating it as primitive. So there are many issues about gender, as I'm sure you know. I think probably I should stress here that even for primitive terms, it's important that you provide examples of what you mean. And if you can elucidate those examples, then that will be helpful. But you shouldn't claim to have a definition when you can't have it. And you shouldn't be afraid of declaring certain terms to be primitive. Most terms in SNOMED, if I understand it, are declared to be primitives. but that's because SNOMED is so big and they didn't really have a coherent strategy for doing definitions. And because medicine is hard, one has to say. So, yes?
In your HL7 examples, those definitions seem to be interpretations rather than definitions.
Which examples are you talking about?
The medication.
The HL7. So HL7, in some of its documentation, describes itself as as being based on something called the reference information model. The reference information model is a model of information. And so if you're modeling information, then you might say disease is information about a disease. The problem is that you then say virus, information about virus causes information about disease. That is not right. And I don't see how to replace that causes by anything which is coherent. And that's the information modeling trick which I've never ever grasped. How do they get information to cause other information? It's not just HL7 that makes that mistake. HL7 is just HL7. So now, I say SNOMED didn't really have a coherent approach to definitions. I think this is the coherent approach. And this is the third thing that I really want you to remember, because this is so easy and so useful. When you're building an ontology, you need to formulate definitions for all your terms. And there is an easy way of at least starting that. You have a term A in your ontology, and its parent term is B. And the ontology that you build should be a single inheritance ontology, which means every term should have maximally one parent. Only the root should have no parents. Every other term should have exactly one parent. So you have an A, which is a B. That should be the beginning of your definition. An A is a B, which, and then you need to fill in this C. So a man is a person which is male. Human being, this was Aristotle's example. Now what you do with the C's is up to you, but you already have a template for creating a definition, which will avoid the use mentioned confusion, because you won't ever be tempted to say an A is a name for an A, unless A is a name. It will avoid confusing ontology with epistemology, because you'll really have to think about whether an absent dimple is a. Okay, so this is a really useful, simple trick. And if I've had an influence on ontology development in biomedicine, it's primarily through propagandizing this simple little trick. It wasn't even my idea. It ultimately was Aristotle's idea, but the person who really promulgated this was the creator of the foundational model of anatomy, who studied Aristotle as a schoolboy in Hungary, a man called Cornelius Ross. Now, what Cornelius pointed out was that if you do it this way, when you're formulating your definition, you are giving a quality assurance step on your ontology, because you have to think about what it is about B's which makes them A's. And maybe you'll discover that not all A's are B's when you try and work out what the C should be. You also get a nice parallel between the definitions as you go down the hierarchy and the hierarchy itself, which is useful for your computing. So, now, when you're formulating terms, in the older days, when people used typewriters, there was a reason for being economical in the length of the typing work you had to do. Databases are very often formatted in such a way that the column headers should be nice and short acronyms. In ontology, there's no reason to be economical with the typography. And the gene ontology has terms which are 3 lines long, and the same goes with SNOMED. So avoid acronyms as far as possible. So very, very rarely should you use an acronym. Avoid abbreviations. So in the clinical world, it's very common to use ellipses. So you say breast, or third breast, when you mean the patient in the third bed along the left-hand side of the ward. Ontology should avoid anything like that. It will be chaos. You should always be painfully explicit. And you should avoid mass terms. Now this is a little bit more subtle. Come in. Avoid. So in 1 minute, I think, if that clock is right. Or maybe you're. Oh no, it's one. I should take